Welcome to the Problems Channel Season 2, Episode 5, the episode in which we will discuss the solution of the mathematical problems S2M5, S2M6, and S2M7. Before we do that, however, please allow me, as a friendly reminder, say that I have put together the Season 1 guide. This is a PDF file available in my GitHub repository completely free of charge. The link to that file can be found in the description or in the comment section to this video. In this PDF file, I have compiled the list of all the episodes that we made in Season 1 with the specific material and the names and the numbers of the problems that we formulate and solve in each corresponding episode. Hopefully, the idea here is that this list of episodes and the corresponding mathematical problems will make the navigation through the material that we have on this channel much more easier and much more pleasant for you. Obviously, I am maintaining right now, as we go along, Season 2 guide. This guide or PDF file is obviously not complete, but you can find it in the same location, and the link to that file will be in the description or in the comment section to this video. From Season 1, Episode 2, we remember that first and foremost, mathematics is an art of telling a story of how and why, first and foremost. Later on and in parallel, mathematics becomes an art of telling a story of how and why, wrapped in the language of logical connectives and or not, two quantifiers, existential and universal, and an implication of P then Q, and later on still, and in parallel, mathematics becomes the study of structure divorced from any specific context, but as authors of the corresponding story of how and why, we need to exhibit creativity, ingenuity, and improvisational skills in order to put that story together. And in some sense, the problem-solving approaches that we have been studying so far help us do exactly that. So far, we have studied the transform and conquer problem-solving approach and reinterpret and conquer problem-solving approach, the corresponding episodes that explain and how to apply these approaches to the process of solving this or that mathematical problem form the corresponding playlists. In other words, I have the Transform and Conquer playlist and the Reinterpret and Conquer playlist. These playlists can be found on the homepage of this channel, and the previous two episodes, this episode and a few next episodes, will form correspondingly the reverse order playlist. That playlist will also be on the homepage of this channel, and the idea here is that these playlists should be helpful in order to study these problem-solving approaches systematically. Now let us come back to the problems S2M5, S2M6, and S2M7. In the previous two episodes, I explained twice in detail how the reverse order problem-solving approach works. If you missed these episodes, it's a good idea to watch actually both of them, and to some extent, as any academic material, it's a good idea to watch all of our episodes in sequence, because again, in Season 1, Episode 2, we explain what is mathematics. In Season 1, Episode 2, we explain how to practice mathematics correctly, and so on. In this episode, I will only explain how the reverse order problem-solving approach can be applied to the process of finding an answer or searching for a solution of a mathematical problem. As a reminder, in the mathematical problem S2M5, the setup was the following. Once upon a time, there lived the king, and a peasant managed to get into the king's palace and ask him for a favor. The king said, "What do you want?" The peasant said, "I know that you have a magic apple garden where on apple trees there grow magical golden wonderful apples, and I want to get as much as I can." The king said yes. the peasant walked to the garden, and on its way to the garden, he encountered 3 guards who were guarding the gates attached to the fences 1, 2, and 3. And each guard said that I want the half of what you have on the way back. And the question in this problem is how many apples did the peasant manage to collect if by the time he walked out of the first gate he had 20 apples. Again, sometimes it so happens that any one given mathematical problem can be solved in several distinct enough ways, and this problem is no exception. For example, in the traditional forward flow of causality, it is very much possible to solve this problem, but because right now we are investigating the mechanics of the reverse order problem solving approach, we suggest that our viewers actually solve this problem both ways, in the forward flow of causality or in traditional forward flow of time, for example, and in reverse order or in reverse timeline fashion. So how do we apply the reverse order problem solving approach to the process of searching for a solution of this problem? Well, the reverse order problem solving approach prescribes that in this case, the mechanical flavor of it, that because we have a well delineated process in this particular problem, where the peasant walks through the first gate, second gate, third gate, collects some apples, and then he apparently walks backwards. Third gate, second gate, first gate, he walks out, he has 20 apples on him. In this specific situation, we may start with not the first scenario when, or the first state when the peasant walks towards the garden, but from the very last moment when the peasant collects the apples and begins walking back and finds himself over here at the final stage with 20 apples on him. What does that mean? The fact that in its final state the peasant has 20 apples on him means that, according to the previously made agreement, these 20 apples represent what? These 20 apples represent 1/2 of what he had prior to approaching the first, let's mark this guy's first, second, and third gate. These 20 apples represent the amount of apples that the peasant had after he walked out, and this is the half of what the peasant had prior to approaching the the first gate right here. Again, remember from the previous episodes, we can search for a solution of this problem by technically recording the peasant walking in through the gates, collecting the apples, and then walking out through the gates and giving each guard his share that they agreed on. And as the mechanical flavor of the reverse order problem solving approach prescribes, what we should do or may do is not start from the very first frame of that movie, but from the last frame of the movie. And the last frame of the movie corresponds to the state where the peasant stands outside the garden with 20 apples on him. If we watch the previous several frames, we see that the peasant walks backwards in some funny way over here, facing the first gate, and because 20 apples represent 1/2 of what he had left after he gave his share to the first guard, that means that at this point, instead of dividing, we do multiplication. So 20 times 2, over here, the peasant had 40 apples on him. Consequently, as the mechanical flavor of the reverse order problem solving approach prescribes, we keep watching that movie in the reverse order, in the direction from the last frame towards the first frame. And now we see that 40 apples is the number of apples that the peasant had on him after he walked through the second gate and gave the corresponding share to the second guard. That means that if we keep watching that movie in reverse order, we watch the peasant walking backwards through the second gate, and instead of again dividing, we do the reverse arithmetic operation and we multiply 40 by 2, because every guard in this setup is asking for 1/2 of what the peasant has. Consequently, 40 times 2 becomes 80. 80 apples is the number of apples that the peasant has immediately before he approaches the second gate. And usually also, what does it mean? It means that 80 apples is what the peasant have immediately after walking through the third gate. Now, if we keep watching this movie again in reverse order from the last frame towards the first frame, we will see that in some funny way, the peasant walks backwards through the third gate over here, and the amount of apples that he has at the moment is not cut in half, but multiplied by 2, through the reverse operation. 80 times 2 is 160, consequently 160 apples. I'll write it down better right now. 160 apples is the amount of apples that the peasant has immediately before he approaches the gate number 3, if we watch that movie from the last frame towards the first frame. And here we realize that these are the first few frames, for example, and the let me see, 160, let's say we'll write it over here, 160 apples is the amount of apples that the peasant has when he collected what he could to carry out on him. Again, when we solve problems in reverse order, it is always a good idea to check our reasoning in the traditional or forward flow of causality, in the forward flow of time. And here we reason or check our work as follows. If the peasant managed to collect 160 apples in the magic garden, then after he walked through the third gate, he had to give 1/2 of the apples that he had to the third guard. 160 over 2 is 80. So when the peasant walked out of the third gate, he had 80 apples on him. Then the guard number 2 collected 1/2 of the apples that the peasant had at that moment. 80 over 2 is 40. So here, approaching the first gate, the peasant had 40 apples on him. And again, the last, or the guard number 1, collected his share of 1/2 of 40. He took 20 apples, and the peasant walked out with 20 apples, which is what we're given in the problem statement. And the answer correspondingly is the peasant managed to collect precisely 160 apples in the garden. And by that virtue, we reason that the peasant had to be quite a strong guy to carry 160 apples on him. And it should be understood that this number can be changed, and the overall essence of this problem is dividing some arbitrary number by 2 on every consequent iteration. And we now understand that the language of this problem can be changed, but the essence of the problem, when we iteratively divide, for example, some number by 2, will be one and the same. Now that we solved this problem, let us take a look at the problem S2M6. As a reminder, in this problem, we were told that some number of apples, that is X apples, were lined up on a table, and between every 2 adjacent apples, one pair, next pair, next pair, next pair, 2 more apples were added. Here we marked these new apples with yellow. 2 more apples were inserted. 2 more apples were inserted between every 2 immediately adjacent apples. And then after this injection was carried out, these apples were lined up in a row, and a similar process unfolded next between every 2 immediately adjacent apples. This one and this one, this one and this one, this one and this one. This time 3 new apples, let's say red ones, were inserted. And then once after that operation all the apples were lined up, we're told that 97 apples were counted in that final set of apples. And the question is, how many apples were on the table originally? Again, it is possible to solve this problem in a number of different ways, but because we're studying the mechanics of the reverse order problem solving approach, we suggest that our viewers solve this problem in reverse order. Again, what does that mean? That means that instead of trying to solve this problem starting from the first state and winding up in the last state, we, again, for example, as a vague idea, film that process of injecting apples between every 2 immediately adjacent apples, and then once that process is done, we stop the movie, and instead of rewinding it, we watch this movie not in the traditional forward flow of time from the first frame to the last frame, but we watch it in reverse order, starting from the last frame towards the first frame, and on each corresponding iteration or on each consequent set of previous frames, we try to extract useful and tactical information that will help us arrive at the answer of the problem. So how can the reverse order problem solving approach be applied to this specific problem? Again, we start not from the first state but from the last state, where we're told that 97 apples resulted in the process of injecting apples as explained above. What tactically useful or immediately actionable information can we deduce from this arrangement of apples? Well, if we analyze what happened, for example, during the last state, then we may see, for example, we can treat this set of apples in blocks of how many? 2 apples in this, for example, state can be considered as old or pre-existing. And the 3 apples over here shown in red, for example, 3 apples, 3 apples, 3 apples, can be interpreted as new apples or new additions. Consequently, when we inject 3 apples between every 2 immediately adjacent apples, we can, for example, treat the red apples as new and the white apples shown over here in white as existing ones, which means that the 97 apples can be looked at as a collection of blocks of 4, for example, 1, 2, 3, 4, like so, and then 1, 2, 3, 4, 1, 2, 3, 4, like so, and then let's say 1, 2, 3, 4, and so on. And in these blocks, we have shown in white the old, so to speak, apple, and 3 new ones. We'll color them with red. 1 old, 3 red. 1 old, 3 red. 1 old, 3 red, and so on. Now, because each such block is 4 apples wide, then what does the number 97 suggest to us? Well, that means that number suggests that if we take 97 and reduce it by 1, we'll get 96. We'll get 96. And in what relationship does the number 96 and number 4 exist? Well, we see that, for example, 96 can be represented as 4 times what? 24. That means that the last state of apples can be partitioned into blocks of 4 apples, and there will be exactly 24 blocks, 4 apples each, and in each block there will be 1 old apple and 3 new ones. And we don't forget the 1 apple over here. Let me mark this guy with 1 for with the green color, which is as a reminder for us. And what does this number 24, 4 times 24 means? That number means that we can throw out from each block of 4 apples, we can throw out 3 new apples or 3 red apples. And what does it mean? That means that we will have 24 apples that were on the table after what? If we watch this movie in reverse order, then these 24 apples will represent which state? They will represent this state right here, this particular state, before the 3 apples were injected between every 2 immediately adjacent apples. And what do we do here? Again, and we'll say over here +1 apple, +1 apple, and in total this will be 24 apples +1, like so. 24 apples +1, 25 apples altogether. Again, we watch this movie in reverse order, and we realize that we can look at the same 24 +1, 25 apples through the lens of blocks of how many apples in each. Again, here we can see that for example, the white apples represent the old or pre-existing apples. The 2 apples shown in yellow are the new ones. So that means that we can form triplets in this set of apples and look at these apples in sets of 3 apples, 3 apples, 3 apples, 3 apples, and so on. And in each block of 3 apples, 2 apples shown in yellow will be new, and the apple shown in white will be what? Will be old. Because we have 24 +1 apples in this case, it is evident that 24 can be represented as what? 8 times 3, where 3 is the number of apples in each block and 8 is the number of 3 blocks in the set of 25 apples plus 1 apple. Again, we perform in this step of our solution the operation that is inverse, or we reverse the steps that were made in this problem if we were watching the corresponding movie in the forward or normal flow of time. Instead of adding apples, we throw these guys out, throw out, throw out, throw out, and so on. And that means what? That means that we will have exactly 8 across the 8 blocks of 3 apples each. We will have 8 old or pre-existing apples sprinkled over here originally, plus 1 apple. So the answer to this problem is 8 plus 1 equals 9. Consequently, there were 9 apples on the table before the process of injecting 2 and 3 apples between every 2 adjacent apples was initiated. Again, it is a good idea to experiment or to check the solution of the problem or our answer with the forward flow of causality and line up 9 apples, inject on the first state 2 apples between every 2 adjacent apples, obtain correspondingly however many apples, and then inject 3 new apples between every 2 immediately adjacent apples as well. And that is a way to solve the problem S2M6 by applying the reverse order problem solving approach to it. Now let us address a slightly more challenging problem, slightly more interesting problem, S2M7. In this problem, as a reminder, we are told that ABCD is a square, as shown over here. ABCD is a square, a good old Euclidean square in the Euclidean plane, and inside that square there picks a point E such that the triangle AEB is isosceles, and the magnitudes of the interior angles of the triangle are 15 degrees each. The angle EAB is 15 degrees, and the magnitude of the angle EBA is also 15 degrees. We're also told that under these conditions, the triangle DEC is allegedly equilateral, as shown over here, which means that the distances between the points D and C, C and E and EAD is one and the same, and that distance is equal to the length of the side of the generating or the parent triangle. So how can this problem be solved with the help of the reverse order problem solving approach? This problem is different with respect to the previous problems because here we do not really have a well delineated process which is recursive or iterative, where similar operation on each next step or on each next iteration is applied to the local material. We're simply told that we're given a square, a point is thrown into it, and under these conditions certain other property of the local objects must be true. Here, using this problem, I would like to highlight the fact that heuristic flavor of the reverse order problem solving approach comes into view, and by analyzing and dissecting the solution of the problem, we'll hopefully understand what does heuristic flavor of the reverse order problem solving approach means. From the previous 2 episodes, you may remember that I mentioned that in the traditional flow of time, we start with what is given, and then by portraying or representing if P then Q implications with the geometric point, let's say this is given, we try to craft a forward flow of causality reasoning this way, we zig and zag somehow, and then we arrive at the material that is sought after. And as the reverse order problem solving approach prescribes, instead of trying to reason from what is given and arrive at what is sought after, we switch the roles of these 2 units of information and take what is sought after as an input and try to reason our way in reverse order. For example, we try to reason from what is sought after towards what is given. And possibly in the previous 2 episodes where I explained how all this mechanism works, it may have been a little bit abstract and not clear, but such is life. It is, in my view, the best way to explain how the reverse order problem solving approach works, by using specifically these terms, if P then Q, and even in even if in some solutions these if P then Q implications are not explicitly present, they're still there anyway. That is why I wrap my explanation of the reverse order problem solving approach precisely in if P then Q implication. Now, as a small historical, perhaps, reminder, the folks who put what we now call mathematical logic together, they made some number of fundamental decisions, and they basically handed these decisions down to us. If you are a middle school or high school student, do not be afraid. This is nothing too complicated. And if you are a student in college in your first years, then it's even more so not complicated. You should be able to handle this. But by the looks of it, the folks who have founded what we now refer to as mathematical logic, they tried to open the door as wide as possible when it came to the construct to which we refer as if P then Q. In this construct, P, the material that is packed into P, is called a hypothesis, antecedent, and Q is called a conclusion or a consequent. And the way the decision many years was made by the people who founded mathematical logic, just about any material, literally any material, can go into P, into antecedent, and into Q, or into conclusion. For example, the construct that looks like this: if, let's say, roses are red, then pi is irrational. This is a perfectly valid sentence in mathematical logic, and overall, if P then Q and this particular instance of it is called a conditional. And in conditional, when I say that any material can go into P and Q, into hypothesis and a conclusion, that means that the normal or usual causality that exists between a hypothesis and a conclusion does not need to be present. Again, this is in some sense an arbitrary decision that was made by the founders of mathematical logic. That is why such a sentence, if roses are red, then pi is irrational, is a perfectly legal conditional. And we'll call it a conditional. In other words, in a conditional, the presence of the flow of causality, or the presence of causality between a premise and a conclusion, is not required. It can be there, but it's not required. More pedantically then, conditional. So conditional plus causality, this, when the causality is present in a conditional, then that formation is called an implication, or an inference, For example, and this is obviously mathematicians in all likelihood do not really work with sentences like if roses are red, then pi is irrational. Here, some roses are red, and we know that pi is irrational. We know even more, pi is transcendental, but in this case, the premise is true, the consequent is true. Overall, this conditional evaluates to true, but from a mathematical point, it doesn't really make any sense. For example, what kind of connection or mathematical causality can be established between the color of a flower and a property of a specific mathematical object? There is no such a causality. But when the causality is present in a conditional, then it becomes an implication and an inference. To give you a slightly more grown-up example, for example, if G is a finite group, then the order of every subgroup of such a group is a positive divisor of the order of that group, where here, for example, K is a whole positive number, that symbolic representation of the fact known as the Lagrange's theorem in the theory of groups. And if this is too much of a complicated information, for example, we can take Euclid's Pons Esinorum, book 1, proposition 5, which says that if a planar Euclidean triangle is isosceles, in other words, the length of these two sides is the same, then the magnitudes of the interior angles at the base of this triangle are one and the same. If a triangle is isosceles, then the magnitudes of the interior angles at the base are one and the same, and in both cases we have a meaningful flow of causality between the material that is packed into the premise and the material that is packed into the consequent. Now, what does it mean? How does all this apply to our problem S2M7? Well, let us reword perhaps that problem ever so slightly and note that in this case we can frame this setup as follows. If this and that is given, then the triangle DEC is equilateral. So in that respect, the consequent in our problem S2M7 is the fact that the triangle DEC is equilateral, and the heuristic flavor of the reverse order problem solving approach suggests that instead of attacking this problem head on and trying to find the solution of this problem from what is given, we begin the search for a solution or for a proof in this particular case from what is required of us, what is sought after. So when a problem has a well-delineated, well-expressed iterative or repetitive process, then we say that with the mechanical flavor of the reverse order problem solving approach, we may begin the search for a solution for that problem from the last stage or from the last state. And this is what we have been doing so far in all the previous episodes which dealt with the reverse order problem solving approach. But because in this problem we do not have a well-delineated process, we begin the search for a proof or for a solution of this problem with what is sought after, or with the fact that the triangle DEC is equilateral. So let me draw perhaps a slightly bigger version of that situation. So we have a square A, B, C, D. Inside that square, we're told we're given a point somewhere here, the point E, in such a way that the magnitudes of these angles are 15 degrees. And in this case, let's say the length of the side of a square is always A. The length of this line segment equals to the length of this line segment, and here this, and these are all by magnitude are the same. So here we begin the search for a solution or for a convincing enough line of reasoning from the fact that or from the assumption that the triangle DCE is already equilateral. Again, this is strictly a convenience maneuver, so to speak. We do not know if that is true or not. Maybe that assumption is not true, but here we act as if this assumption is true, and we try to generate enough tactically useful information for a traditional or forward flow of causality if we can construct one and extract it from the maneuver of reasoning in reverse order. So now we take it as a true statement or as a mathematical fact that in this particular setup, the triangle DEC is equilateral. Here, again, there is no well-expressed process, repetitive process, or iterative process. And that is why it is not so straightforward to just plug the numbers, start with plugging the numbers from the very last state as we have been doing before, and then using, for example, inverse operations, addition instead of subtraction, division instead of multiplication, and so on. So that is why I refer to this particular setup as heuristic flavor of the reverse order problem solving approach. There is no algorithmic guidance to how exactly to unwind our steps from what is sought after towards what is given. It all depends on our experience, on the depth of mathematical knowledge, and so on. But in this case, what kind of tactically useful and immediately actionable information can we extract from the assumption that the triangle DEC is already equilateral? Well, for example, one actionable unit of information that we can extract from this is the following one. Look at the triangle, for example, ECB. What does this triangle tell us? Because this triangle is equilateral, DEC. We have the length of its side here. DC is the length of the side of a square. In a square, the length of all the sides are the same, which means that the length of the line segment CE, this side, and the length of the line segment CB, this side, is one and the same. And consequently, we know by Euclid's Pons norm, or Book 1, Proposition 5, that this triangle is isosceles. And then again, if a triangle is isosceles, then the magnitudes of the interior angles at the base of this triangle are one and the same for the sides that lie opposite these angles. For example, this angle and this angle must be the same. Now, what other tactical useful information can we extract from this observation? Well, if this triangle, again, by assumption, is equilateral, and this is our input into the heuristic flavor of the reverse order problem solving approach, we take this as a given and try to reason our way backwards towards this little triangle. Then the magnitudes of the interior angles of these triangles in terms of, let's say, we'll reason in terms of degrees, it's easier this way, is everywhere 60 degrees. The interior angles, the magnitudes of the interior angles in a square are what? 90 degrees. 90 minus 60, that means that this angle over here is, let's say, 30 degrees. So far, so good. And we just showed that this triangle must be isosceles from this initial assumption by Euclid's Book 1, Proposition 5. If a planar Euclidean triangle is isosceles, then the magnitudes of the interior angles at the base are equal. So this angle by magnitude equals this angle. And what is this angle? Well, the magnitudes of the interior angles of every planar Euclidean triangle sum to 180 degrees. 100, let's do it here, 180 degrees minus 30 degrees equals 150 degrees. 150 over 2 is what? 75. So in this case, then 75 degrees is the angle, 75, of the corresponding angle CEB and CBE. So now, what other useful information can we extract if we keep unwinding our observations in reverse order and we step away further and further from the initial assumption? Well, here that becomes evident why I call this flavor of the reverse order problem solving approach heuristic. We do not really have any specific highly precise algorithmic guidance. We just have to take in the local material as a whole and try to extract useful information from it. So now we'll look at this situation that's unfolding based on our initial assumption that the triangle DEC is equilateral. And what do we say? 60, 75, 15. Are these numbers suggestive or what? 60 plus 15 gets us exactly what? 60 plus 15 gets us exactly 75. So maybe, and this is again where the heuristic and wishful thinking part of generating a reverse order reasoning comes in. So probably 60 is hiding somewhere within the 75, because again, 75 degrees can be represented as 60 plus 15. Again, let's be honest and upfront over here. There is no algorithm that says, oh, this is how you have to do it. 75 can be represented in many different ways. But because of our initial assumptions that we made over here, and from these specific numbers, we do not know yet that this angle must be 15, even though now we do. We prove that the interior angles must be 65. The interior angles of every square are 90 degrees. 90 minus 75, 15. So, we know that this angle must be 15. And if we do the same reasoning over here, we will say that, okay, this guy, the magnitude of this angle is 75 degrees, and this must be 15. What's going on? This is 15. This is 15 degrees. So from this setup, the converse of Pons Asinorum, or the converse of Book 1, Proposition 5, is actually Book 1, Proposition 6 in Euclid's Elements. That's the converse statement, which says that if the magnitudes of the interior angles at the base equal one another, then the lengths of the sides of this triangle that lie against this angles must also be the same, and the corresponding triangle will be isosceles. So now, from the assumption that DEC is a triangle that is equilateral, we arrived at the idea, or at the fact, that this triangle AEB indeed must be isosceles with the magnitude of the interior angles equal to 15 degrees. So this observation right here is again heuristic. It's not algorithmic, admittedly, but we made it once we started reasoning about what we have in reverse order, starting from the material that is sought after and trying to unwind the steps back towards what is given. And further, how can this representation of 75 degrees be converted into a tactically useful information? Again, there is no algorithmic guidance over here. That much should be understood. Everything that we do here depends on the problem-solving experience, the level of mathematical maturity, the level of depth of mathematical knowledge of different vaguely defined layers, and so on. So here we have a 60 degrees and 15 degrees. And we are staring at, in this case, at number 60 that is all over the place in an equilateral triangle. So what tactically useful idea, a happy thought, in the words of Poya, can visit us over here? 60 plus 15, 75. And we have two 75-degree angles. So somewhere here, the 60-degree triangle perhaps is hiding. So what will happen, and this is again in real time, it will not happen right away. We may try and fail many, many times. And eventually we may to come to this happy thought. What if another equilateral triangle with the magnitude of interior angle of 60 is hiding somewhere over here? What will happen? Well, let's see. If we construct a, let's say, which way will it go? Here, for example, we have to make the length of these sides roughly the same. In other words, this the length of this line segment EB. Let's name this point, for example, F, right? What is this? A, B, C, D, E, F. So this will be F, the point F. As a matter of fact, let me try to paint it red, F, for a happy thought. So if we manage to stumble upon this happy thought that, maybe 60 over here is what leads to a 60-degree or equilateral triangle constructed on that side, simply because, again, 15, 60, 75, 90, all these numbers are happily coexist over here in this corner. What will happen? This is 60 degrees, then this will be 60 degrees, this angle will be 60 degrees, consequently this angle again will be, because this is 75, this will be 15. So what do we see here then? Then again, there is no algorithmic guidance, but a happy thought, a hypothesis comes in. If this angle FBC is 15, this triangle EBF is equilateral. What does it mean? If the triangle ABF is equilateral, that means that the length of all of its sides EBBF, FE are the same, but the length of the side EB is one of the central characters in our triangle with the 15-degree interior angles here, this angle and this angle. And that means that the length of the line segment EB is the same as the length of the line segment BF. And the angle over here, FBC, is a 15-degree angle. What next step can we make in this reasoning? Of course, if we finish, so to speak, the construction of this triangle, then it looks like this line segment FB by length will be the same as FC, and that angle over here will also be 15 degrees. Simply because, again, we have as a starting point a triangle, the triangle AEB, with the magnitudes of the interior angles here 15 degrees, and the length of the line segment EB is the same as the length of the line segment FB and BF. And now, depending again on our experience, we may realize that we already generated enough of a tactically useful information, and in some sense, again, here this triangle CF, this guy right here, CFB, let me probably even cross hatch it so you guys can see it better. This triangle CBF can also be an auxiliary object when we flip our reasoning and construct a forward flow of causality proof that is actually required. So, for example, let's say if you are in middle school or in high school or in college, you're taking a Euclidean geometry course. This problem was given to you as a homework assignment, and the professor in college or your math teacher in school called you to the blackboard and asked you to present your solution of the problem, and that is how you will present your solution of the problem in the forward flow of causality, you will say things like this. Given the setup of the problem, as explained, A, B, C, D is a square. The point E is taken inside. The triangle here is isosceles. And we're to prove that the triangle DEC is equilateral. So what will we do? Here we construct, because we can, a helper isosceles triangle, but not on the side BA or AB, which is given to us, but we constructed on the side CB in such a way that the triangle, let's write it over here, the triangle CFB is isosceles. So this length equals to this length. The length CF equals to, let's write it down, CF equals to FB. And the corresponding angles are 15, let me just write it down, 15 degrees here, and over here it's 15 degrees. In other words, we construct an auxiliary triangle CFB, which is congruent to the triangle EAB, because again we can. So in this case, when we present our forward flow solution to our classmates, then we do not have any of this information. This information is not available to us. We cannot say anything about this yet. But what we do have is a square, a given point E inside, the fact that the triangle AEB is isosceles, and as a forward flow of causality, as our homework, we present to our class, our solution, and we begin it with the construction of an auxiliary triangle CFB that is congruent to the triangle AEB, and this is what we have right now. Then we reason as follows. If this angle is 15, and this angle is 15 by construction, this angle is 15 by what is given in the problem statement, and the length of this line segment EB, let's write it down here, we have EB is equal to FB, right? EB is equal to FB through the magic of our auxiliary or a helper object. Now, what can we say about the triangle EBF? Well, we know that if the magnitude of this angle is 15, the magnitude of this angle is 15, the magnitude of the interior angle in a square at the vertex B is 90. 90 minus 15 plus 15, 30. 90 minus 30 is 60. Then the magnitude of this angle must be 60. But as we just said, if a Euclidean planar triangle is isosceles, which this triangle certainly is, then the magnitudes of the interior angles at the base of that triangle must be equal. In other words, in this triangle, this angle and this angle must be the same, and we know the magnitude of these angles. 180 minus 60 equals 120. 120 over 2 equals 60 degrees. In other words, we deduced or proved in the forward flow of causality that the magnitude of this angle is 60 degrees also, and we just proved that correspondingly the triangle EBF must be what? Must be equilateral. So this angle, this length, the one is the same. But what does that mean? That means that because the length of this line segment EF is equal to the length of the line segment FB, and FB is equal, the length of FB is equal to the length of FC over here. That means that the length of the line segment EF, let's write it down here, EF is equal to the length of the line segment FC. So far so good. That maneuver should be understood easily because this triangle EBF is equilateral. The triangle, the auxiliary triangle FBC is isosceles, and because the length of this line segment is equal to the length of this line segment, it means that the length of the line segment EF must be equal to the length of the line segment FC. Now, what else can we say about then this angle? Let's mark it as X. Well, we already know that if the magnitudes of these angles are 15 and 15 is 30, 180 minus 30 is 150. So the magnitude of the angle, let's write it down, angle CFB must be 150 degrees. CFB, that angle by magnitude must be 150 degrees. And if this angle is 60 degrees, what is the magnitude of this angle? Well, we know 150 plus 60 equals 210 degrees is this angle right here. And then the angle X by magnitude is what? 180 minus 210 equals to, I'm sorry, 180. My bad. 360. The entire angle is 360, of course. 360 minus 210 comes out to 150, right? 150. So this angle is 150 degrees. And if the triangle CFE is isosceles, that means again the magnitude of the interior angles here, maybe let me write it for show the thread, this and this must be what? Again, 180 degrees minus 150 degrees equals 30 degrees, and 30 degrees over 2 equals to 15 degrees. So the magnitudes of these angles, this angle is 15 and this angle is 15. But, and this is what we proved formally in the forward flow of causality, but we already know that the magnitude of this angle is 60, the magnitude of this angle is 60, the magnitudes of the smaller angles are 15 degrees each. 60 degrees plus 15 degrees is 75 degrees, and that means that the angle, the magnitude of the angle CEB, the magnitude of the angle, let's see, CEB equals 75 degrees, and at the same time, this is what? This is the magnitude of the angle CBE. Angle CBE. In other words, we just proved in the forward flow of causality that the triangle ECB must be isosceles because the magnitudes of the interior angles at the base of this triangle are one and the same, and this is the converse of Euclid's Elements Pons Asinorum Book 1 Proposition 5, or part of it, known as Book 1 Proposition 6. Now, if this triangle C, so the triangle CEB is such that CE, the length of the line segment CE, is the same as the length of the line segment CB, which is to say that this triangle is isosceles, And if this triangle is isosceles, then the length of the sides that lie against the equal angles must be the same. So this, the length of this side of this triangle, and this side must be one and the same. And voila, as if by magic, if the length of this side is A, the length of this side is A. But we just proved that the magnitude of this angle ECB is 30, and the magnitude of the interior angle of the square at the vertex C is 90. So what is the magnitude of the angle DCE? 90 degrees minus 30 degrees equal to 60 degrees. And the triangle DCE is certainly what? The triangle DCE is certainly isosceles because the length of this side of this triangle equals to the length of this side. We just proved that. And again, we have a isosceles triangle with the interior, with the magnitude of its interior angle at the vertex as 60 degrees. Consequently, the magnitudes of the interior angles of this triangle that lie opposite to the equal sides, this side is this side, must be the same, and their magnitude is recovered. We know how. 180 degrees minus 60 degrees equals 120 degrees over 2 equals to 60 degrees. So the magnitude of this angle is 60 degrees, the magnitude of this angle is 60 degrees, and voila, such a triangle is indeed equilateral. And we prove that given the input material as stated over there, it is the case that the triangle DEC is equilateral, and the length of the sides of this triangle are all the same, and the magnitudes of the interior angles are 60 degrees. However, when you present this type of proof, either your Euclidean geometry professor or your math teacher in school will have no choice to admit, yeah, this is correct, but all your friends in the class will be wondering or will be lost. Where did this happy thought, or where did this auxiliary triangle FCB, where did it come from? Because you remember that you presented your proof out of the blue, so to speak, and this proof is correct, but you omitted all the motivation for the introduction of this auxiliary helper object, which made the proof, in this case, very straightforward. It's just, in a sense, chasing the angles and using the Euclid's Elements, Book 1, Proposition 5, Pons Essenorum, and its converse, Book 1, Proposition 6. That was all that there is to it. So your friends and your math professor will probably know, but your friends in the class to whom you presented this forward flow of causality proof will be lost. Where did this guy get this auxiliary triangle CFB from? Well, now in this episode we showed and we know that the happy thought for the introduction of this auxiliary triangle that made the forward flow of causality proof quite straightforward came precisely from the application of the heuristic flavor of the reverse order problem solving approach. And again, in summary, if you feel that you are lost and that was too much, here we took the consequent Q, or the fact that the triangle DEC is equilateral, as our input, as the fodder for backwards reasoning or for reasoning in reverse order from the fact that this triangle is equilateral towards the fact that this triangle must be isosceles. Then we arrived at the premise, and by the time the very journey from the consequent to the premise helped us or provided us with immediately actionable or useful tactical material, which we then converted into the introduction of an auxiliary object, a helper triangle CFB, and now we realize that, the forward flow of causality will now be very straightforward. But again, in general, it takes some powers of perspicacity to introduce this helper triangle, which makes the solution straightforward because it's nothing more than chasing angles and applying the theorems that relate to an isosceles triangle. Again, if you have any questions, then possibly rewind and watch this segment several times, or post your questions in the comment section to this video. For now, this is it for this segment, and we will move on to the next several challenges that will address the heuristic flavor of the reverse order problem solving approach. In our next two challenges, we will deal with the problems, with the mathematical problems S2M8 and the mathematical problem S2M9. In case if you joined our channel later in time, then with the letters M, we designate the problems in mathematics. With the letters P, we designate the problems in physics, and with the letter CS, we designate the problems in computer science. And we also show in which season this or that problem was introduced. Consequently, S2M8 is the mathematical problem number 8 that was introduced in the season 2, and this problem is a mathematical problem number 9 that was introduced in the season 2, and so on. In the problem S2M8, we're given the following setup. We're given a trapezoid A, B, C, D, and we're told that its diagonals A, C, and B, D intersect at a point O as depicted over here. The straight lines AC and BD intersect. This is a symbol that we borrow from set theory. So the straight lines AC and BD intersect at a point O. We're also told that we're given two extra circles, the circle S1 and the circle S2, in such a way that the circle S1 passes precisely through the points O, B, and A, and the circle S2 passes precisely through the points O, C, and D. In other words, each of these circles passes, for sure, through the two corresponding vertices of the trapezoid. The circle S1 passes through the vertices A and B, and the circle S2 passes through the vertices CD of our trapezoid ABCD. Both of the circles intersect, and circles intersect at two distinct points. The point O, which we already accounted for, and we're also told that the circles S1 and S2 intersect at a point M, which sits precisely, not somewhere else in the plane, but the point M, the second point of intersection of the circles S1 and S2, sits precisely on the base AD of the trapezoid ABCD. This is the fact that we reflected with this symbolic string. The circle S1 and the circle S2 again intersect at or intersect over a set of 2 points O and M, of which the point M belongs to the base AD. And the challenge in this problem is, given this setup, show that the triangle BMC is isosceles in such a way that the length of the side MB, here I've showed that the BM, equals to the length of the side CM shown over here. The length of the line segment BM is equal to the length of the line segment CM. So the length of these two sides in this triangle, presumably, again, we do not know yet, but presumably they are equal. In the problem S2M9, we are asked to generate two mathematical algorithms, and given two circles S1 and S2, we're asked to come up, synthesize, construct, generate an algorithm that allows us to construct two external tangents to these two circles, which, again, to be perfectly clear, in the same Euclidean plane, we're given two circles, S1 and S2, which means we're given the center O1 of the circle S1, and we're given the location of the point O2, which is the center of the circle S2. And consequently, we know the length of the radii, the length of the radius R1 of the circle 1, and the length of the radius R2 of the circle S2. And we are asked to construct an algorithm according to which the two external tangents to these circles can be recovered or can be constructed. Again, the external tangents, in contrast with internal tangents, do not intersect the line segment O1, O2 that connects the centers of the given circles, but if the so-called line of centers continued indefinitely, then in one direction, these two tangents, the external tangents, will, of course, intersect that line segment extended. And again, we are interested in the general case when, of course, it is possible to construct external tangents. For example, when the smaller circle S2 is fully contained or located inside the larger circle S1, then it is not possible. We're not interested in that case. If the length of the radii of the circles are exactly the same, then it is also not that interesting, but you can account for it. Here, what we are interested in is in a substantial case when, let's say, as a convention, the circle S1 is larger than the circle S2. In the second part of this problem, we are asked to do the same for internal tangents of two circles, again, when, of course, it is possible and meaningful to talk about internal tangents. And the difference between the internal and external tangents is the following. Internal tangents to two circles, when they exist, they precisely intersect the line segment O1, O2 that connects the centers of the two given circles. Now, just to make your life easier and make sure that you remember the new material that we covered in this episode, over here on the top, I wrote the bare minimum amount of information about the construct known as if P then Q a conditional or an implication. Again, if you are a student in middle or high school, do not worry about it. This is not too complicated. This is simply a number of, in some sense, arbitrary decisions that was handed down to us by the people who came before us, the people who founded what is now known as mathematical logic. So it just takes a little bit of time to understanding what the rules are and digesting the terminology. This is nothing beyond the capability of a middle school or high school student. And if you're in college, you already supposed to know this, and if you do not know, then again, it wouldn't hurt and it's not horribly complicated. As such, in the construct if P then Q, the material that is packed into the clause that sits between if and then over here is called a premise, a hypothesis, or an antecedent. And the material that is packed into Q, or the clause that sits behind then, is called a consequent or a conclusion. Again, as an arbitrary decision by the folks who founded the what we now call mathematical logic, it was taken that there is no need for a meaningful mathematical causality between a premise and a conclusion. For example, this causality can be present, but it's not required. Consequently, funny sounding phrases like if roses are red, then pi is irrational, they are completely legal and valid conditional statements. Conditional statements because, again, what type of causality can we possibly find between the specific color of a specific flower and a property of specific property of a specific mathematical object. There is no flow of causality. Consequently, this instance of if P then Q construct is called a conditional. However, when the causality, when a meaningful mathematical causality is present between the material packed in P and material packed in Q, a premise and a conclusion, then this construct becomes an inference or an implication. And in the heuristic flavor of the reverse order problem solving approach, when we do not have a well delineated process, iterative or repetitive process, we suggest that we begin our solution not with the premise, but with a conclusion, taking the material packed into the conclusion of this specific statement as an input or as a fodder, and we try to reason our way backwards towards what is given. Again, this is not, of course, a direct solution, but this is a helper process that may help us generate the required steps, which will constitute the forward flow of causality, and this is what's sought after in such problems. So, for example, let's say we decide to solve this problem using the heuristic flavor of the reverse order problem solving approach. In these two little problems, what is the premise and what is the conclusion? Well, the premise in both problems is the following material: one and the same Euclidean plane, two circles, S1 and S2, that sit in this one and the same ambient Euclidean plane. The locations of the points O1 and O2, which play the roles of the centers of the circles, is known, is given to us. That's the material that's packed into the premise of this problem. And what will be the consequent? Well, the consequent in this case will be a set of steps or a mathematical algorithm according to which we will be able to construct the external tangents to these circles S1 and S2. Consequently, if we decide to solve this problem by applying the reverse order problem solving approach to the process of unlocking a solution of these problems, then what will we take as given? Well, in the first case, we will take as given that these straight lines that are tangent to both circles are already given, an all-knowing, a perfect logician, a perfect and infallible computationalist, the mathematical oracle, somehow already told us, here, you have it. You have these two straight lines that are external tangents. Go. So we'll take this as our input, as an initial line of reasoning, and then we'll try to unfold, we try to reason in reverse order and somehow find the actionable material in this assumption that will allow us to construct the forward flow of causality solution, because again, this is always the goal, the forward flow of causality, and the application of the reverse order problem solving approach is just a temporary step or a stepping stone that will allow us to unlock or find that forward flow of causality solution. And in this part of the problem, we'll assume that internal tangents are already given to us by the mathematical oracle as already solved problem, and then we'll try to somehow reason our way backwards into these two circles before these two internal tangents came into existence. Likewise, if we decide to solve the problem S2M8 by applying the heuristic flavor of the reverse order problem solving approach to it, what will be the initial point of our process B? Well, the initial point of this process will be the consequent. And what is the consequent? In this problem, the consequent is the case that, or the statement of fact that the triangle BMC is isosceles. As such, we will say, if temporarily, and we do not know if that is true, but assuming that this is true, that the triangle BMC is isosceles, then what type of tactically useful information can we uncover from that assumption? And once we come back to what is given to us, can we flip this reverse flow of causality and somehow mix it and shake it into the forward flow of causality and generate the required proof? This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss the solutions of the problems S2M8 and S2M9.